So good morning. Welcome to classroom. We'll continue with our discussion on solving differential equations with constant coefficients. Take up the case of higher order linear ODEs with constant coefficients. In fact, we have completely worked out this problem because you know that one can transform higher order equations into first order systems, and there is an equivalent first order system of equations that you get for a given higher order equation. And then of course you can apply the theory that we have developed to find out the solutions of the system, and you see that the first component of the solutions always give you the solution. So once you get a basis for the solution space or a fundamental set of solutions for the equivalent system, what you do is you take the first component of those solution vectors. They will form a linearly independent system of solutions for the higher order equation. Now this essentially solves it, but one can directly give this method because that is more easy to do. In fact, it's just a repetition of whatever you want to do, but we are not going to the process of converting this first into an equivalent system and then working on it. So let us consider the following homogeneous nth order linear differential equation. So let defined as where AIs are constants. And first, in general, we would like to solve equations of the type equal to 0. That is the inhomogeneous equation that we want to look at. Now the method is, of course, you get a general solution of Lx equal to 0. So we have to construct a fundamental system set of solutions Lx equal to 0, and then find a particular solution of zero. Here we use method of variation of parameters, or the method of Green's function, to get the particular solution. Then a general solution is of the inhomogeneous, non-homogeneous linear problem is a general solution of the associated homogeneous problem plus a particular solution. So we shall use a direct method to find the general solution. That is, you call this 1, call this 2. So that's the procedure. Now, as I said, we can convert this, transform the problem to an equivalent system it's a linear system that you end up with. Linear first order system and apply the theory we have considered earlier. But we shall directly consider the higher order equation. So denote this by Okay. Now what we observe is this. We observe that the characteristic equation associated with 1, three, or equivalently with the equivalent is p lambda n minus. That is an nth order polynomial with so if we set d by dt, then 1 takes the form p dx and 3 equal to 0. Now we can split the polynomial p into, so in C now you see that in C the polynomial splits into linear factors. So we can write down the factorization. We have C, then there exists complex roots, distinct roots, K such that of P so that P lambda is equal to Mj, where algebraic multiplicities are oh, so this is something that we get. Accordingly, is equivalent to bracket we write m1 plus n, which is the order of the equation. Yeah, so that is the way in which it comes. Therefore, P dx equal to 0. So we see that these factors, they do commute. Okay, since the factors commute, P dx equal to 0. D minus equal to 0. Equal to 0. So if we can get sufficiently many, that means you know that the solution space of P dx equal to 0 is an n-dimensional vector space. Okay, so the set of all x which consists of all those x belonging to Cn, or yeah, n times continuously differentiable on with is an n-dimensional vector space. This we know. Therefore, it is quite easy to work on that. So, it is enough to find a basis consisting of n independent solutions of this problem. Try to find if possible n linearly independent solutions of d minus lambda I to the power mi equal to 0 for now these lambda i's may be non-real. Okay, lambda i's are generally in general complex numbers. So that's a basic problem. So can we do this? This is the question. Okay. Now we try to solve equations. Therefore, the problem reduces to at the first stage solving and then for various values of lambda and m's we can write down the solution. Okay, right. So let us see how we can do this. Okay, we make the first observation. The first observation that we make is this. Okay, so you have earlier seen this and elaborately worked out this. We observe that this we have proved earlier. D minus lambda to the power m e to the power this is equal to e to the power lambda t this can be proved by induction. Consequently, we have the following. That is what we want to use. So you get this is equal to 0 implies, see, one can apply this result, this identity, and from that you get d to the power m e to the power minus lambda t equal to 0, and this implies, see, now this is simply differentiation, so the mth derivative of this function is equal to 0, so this implies e to the power minus lambda t xt equal to, where p is a polynomial, of degree minus. So now you see we have got enough functions coming from here. Okay, right. Therefore, what do we get? So we have to solve this for each I. Okay. Therefore, d minus d to the power, okay, what is it? D minus lambda I to the power mi of x equal to 0, 0 implies equal to xt equal to PIT e to the power lambda I t, where degree of Pi is so all these are solutions. Now you can use your lambda 1, lambda 2, etc., lambda k and the Pi's. Plenty of polynomials here, and these are with arbitrary coefficients at the moment. Now the question is the following. Okay. So we take, okay. So we can get the solutions of this form, that we have xt equal to p, we'll write like this, where, okay, we'll keep it like that, where p mi minus 1 t is a polynomial So what we get the following function. So consider j minus 1 lambda it for j equal to mi. Look at this set of functions. They all satisfy, for all these functions we have PD of I running from 1 to k is corresponding to lambda 1, lambda 2, lambda k. So since we have equal to n, we have n functions satisfying the equation. So the question that we ask is this: do they basis for the solution space of solution space which is n dimensional. dimensional. Which is n dimensional. So there are n such functions now, sorry, n such vectors now. So we have to check whether they form a linearly independent set of solutions.